Hi, this is Sam McCrossan, and today I'm going to be talking about sound waves. Sound is very important because hearing is one of your five senses, and everything you've ever heard has been the result of a sound wave in some form. However, for being such a basic part of human life, it is surprisingly complex and there are many misconceptions about it. There are entire college courses devoted to studying acoustics and sound and how it works. However, we don't quite have that much time, so today I'm just going to give a general overview of how it works. To start, sound that you hear is just a pressure wave that travels through the air like vibrations. Many different things can create sound, such as vocal cords that create vibrations in your throat that then travel through the air to the listener's ears. Things that often come to mind when thinking about sound are musical instruments. Musical instruments can create sound just by plucking them or blowing air through them, and this creates vibrations that can travel through the air to our ears. Likewise, speakers and headphones can create sound very easily, and they do so by having a cone inside of a casing that vibrates quickly thanks to a magnet. Just like there are three primary colors that can be mixed to create every color imaginable, there are four primary sound waves that can be mixed to create every possible sound imaginable. This is why speakers can create such a variety in sound using only one small device. The four basic types of sound waves are sine waves, square waves, triangle waves, and sawtooth waves. Long ago, someone much smarter than I figured out that by combining these four waves in different ways, you can create every sound imaginable. While these graphs represent how each of the waves is interpreted, they don't actually look like that traveling through the air because they are a wave of pressure. Now, whenever an object vibrates, like let's say a tuning fork, when the object flexes outward towards the air, it compresses the air molecules surrounding it. Then when it flexes inwards away from the air, it creates an area of low pressure in the molecules. These areas of high and low pressure then travel outwards like waves in the ocean, and they're called compressions and rarefactions, compressions of course being the more compressed part of the air. The typical graph of a sound wave then measures the pressure in the air from a standing point. When a compression passes over the point, the graph goes up to show that there is increased pressure, and when a rarefaction crosses over the point, the graph goes down to show that there is decreased pressure. At this point, you're probably wondering how all of this ties back to chemistry. Well, chemistry is classically defined in the dictionary as the branch of science that deals with the identification of the substances of which matter is composed, the investigation of their properties and the ways in which they interact, combine, and change, and the use of these processes to form new substances. Certainly, everything I've talked about so far has had to do with matter and its interactions with other matter, so therefore falls under the branch of chemistry. You'll also notice that a graph of a sound wave looks surprisingly similar to something else we've studied in chemistry, light. That's because sound waves and light waves are measured in much the same way. They all have amplitude, wavelengths, and frequencies. Unlike light, however, sound travels at its own unique speed in every different substance that it passes through. The general equation for the speed of sound is given by speed equals elasticity over density. We're all familiar with density, although some of us might not be familiar with elasticity. Elasticity is simply an object's ability to resume its normal shape after being stretched or compressed, or the object's stretchiness. For example, air has very low density, but also has very low elasticity, which means sound can only travel through air at about 340 meters per second. Aluminum, on the other hand, has very high density, but it has very, very high elasticity, which gives sound the ability to travel through it at almost 5,000 meters per second. Also on the note of the speed of sound, there's also something called Mach speed. You've probably heard of Mach speed if you grew up watching Jimmy Neutron like I did. Mach speed is simply the speed at which sound travels in any given medium. As previously mentioned, the Mach speed in air is about 340 meters per second. In conclusion, there is a ton to sound, most of which I didn't even scratch the surface of in this video. If you want to know more about sound, feel free to read my paper or feel free to ask me questions on it. I'm a sound engineer and it's what I love to do and it's what I love to talk about. Thanks so much for watching and have a good one.